Okay, this is OCR 2021 AS Level Physics Paper 2, Depth in Physics. Let's go. Two loudspeakers, S1 and S2. Sounds like this is going to be interference, double slit, as it were. What is meant by coherent? Well, I think that saying in phase is okay, but the proper term is constant phase difference between waves, but we don't really need that. Constant phase difference is fine. We have points here. Oh gosh, right. Distance between S1 and J is 2 meters, so that's 2 meters. And then we're told to K is 2.05 meters. Okay, well, we're just being asked for the path difference at J to begin with. So that's 2.08 meters. And we're told that that is 2.21 meters. So we're talking from S1 and S2 to K. So we know the two distances there are 2.08 and 2 meters. So therefore, the path difference, the difference in the distance, is just going to be 2.08. Take away 2 meters, and we know that's just going to be 0.08 meters. Nice, easy start. State the phase difference in radians at point J. Well, we know it's the first minimum, don't we? So a minimum means destructive interference, so that must mean that therefore the phase difference, we could say phi OCR, like saying phi is going to be equal to half a wavelength. So in other words, pi radians out of phase. So the wavelength of the sound waves is 0.16 meters, 0.16 meters. Well, that's easy, isn't it? We know that pi over 2 is equal to 0.08 meters. Therefore, lambda is equal to 0.16 meters. Awesome. C, the frequency of the sound is determined using the oscilloscope. Explain how the oscilloscope is used to determine the frequency. So we read x-axis, which is time. What we do is find time period by measuring between two adjacent peaks. 2 marks? Yeah, I mean, they've said you need to mention time base. I think that's a bit mean. We need to say using time base. But I mean, that's a given, isn't it? It's like, oh yeah, we've got to turn the oscilloscope on as well. We don't need to mention everything. I think that's me, whatever. Right, we have the frequency there, and we're looking for the speed, so therefore we know that V is equal to F lambda, so that's equal to 2100 times the wavelength, which you said was 0.16. I feel like I can do that in my head, but I'm not going to do that. That's 336 meters per second, which sounds pretty on brand for sound waves. 2, force against extension graph for piece of rubber. State the physical quantity represented by the area under the loading curve. That is energy. If we wanted to be specific, we could say elastic potential. But again, it depends whether it's being loaded or unloaded. But yeah, it is being loaded at that point. Determine the energy E transferred when the rubber is stretched to an extension of 0.25. Are you kidding me? Are we going to have to count squares? Oh no. Oh, you're going to be kidding me. That's so many squares. Can we just do like big squares? No, we can't do that. Surely not. We can't just use half FX because that's only for a straight line, isn't it? I think they might have split it up into half squares actually. So they've basically done this. Okay, so I guess, yeah, big squares, that's going to be too inaccurate. Small squares, that's going to be way too long. That's going to take way too long. So let's go with half squares then, I guess. Each square is going to be equal to, well, just the height of one of these times the width of one of these. So it's going to be 2.5 newtons times 0.025. And so that gives us 0.0625 joules per half a square there. Should we count these then? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's 18 whole ones. I'm going to say 19, 20, 22, 23, 24, 25, 26, 27, whoops, 28, 29, 30, about 31. Well, that is what they've got, so fair enough. 31 times that. That gives us 1.9 joules. So yeah, I guess if little squares are taking too long, big squares are too inaccurate, then go for half squares instead. Good compromise. Suggest why the energy transfer by the rubber during unloading is different to your answer. In that, it's because some energy is transferred to the surroundings as heat. Again, it could be to the rubber, but I guess that's included in surroundings, I guess. Metal wire has a length of that, cross-sectional area of that. We have a weight, so a force, and we have a Young modulus as well. So calculate the stress in the wire. So stress is equal to force divided by area. So that is 49 divided by 1.4 times 10 to the minus 7. And that gives us 3.5 times 10 to the 8 pascals. The strain E of the wire, well, we don't have the extension, so we're going to have to just say Young modulus is equal to stress over strain. Therefore, swapping this round, swapping these two round, strain is equal to stress over the Young modulus. So that's going to be 3.5 times 10 to the 8 divided by, what's the Young modulus? 180 gigapascals. So 180 times 10 to the 9. So I guess we could just say that, well, that's 10 times 10 to the 1 down the bottom there. So in other words, 3.5 divided by 1,800. And that gives us 1.94 times 10 to the minus 3. So let's just say 1.9 times 10 to the minus 3. The extension, well, we know that strain is equal to change in length over original length. Therefore, extension is just going to be equal to strain times the original length. So that's 1.9 times 10 to the minus 3 times, what was the original length? 2.2. So it's going to be roughly 4, methinks. So that's 4.2 times 10 to the minus 3 meters, 4 mil. The wire in B is replaced by a wire of the same length, so length stays the same, and Young modulus stays the same as well if it's the same metal, but double the diameter. So if it's double the diameter, that means that the area goes up by times 4, doesn't it? Because we know it's pi r squared or pi d squared over 4. State and explain the change, if any, to the elastic potential energy of the wire. Well, we know that, well, if it obeys Hooke's law, then that means that, well, we know that Young modulus is equal to FL over A delta L. So we want to know what's basically happening to that, don't we? So swapping these two round, we can say that delta L is equal to FL over A E. What's staying the same? E staying the same, F and L. So therefore we can say that delta L is proportional to 1 over A. Therefore, delta L goes down by 4. So it stretches 4 times less, which makes sense, doesn't it? Therefore, we can say that energy is equal to half Fx or half F delta L, whatever. Let's say delta L, so you know we've used it there. So therefore, energy also decreases by a factor of 4. 3, we have a linear air track. Gliders, there we go. Massive A, we have massive B. Oh, gosh, this looks like a nightmare. 2 experiments can be carried out. So glider B is initially at rest, and then glider A passes through and then goes, and then glider A rebounds, and so it goes back like that, whereas then glider B goes on like that, and then we have them sticking together. Okay, explain the results of the 2 experiments. Right. With the help of calculations and terms below. Okay, not too bad, not too bad. So we can say, first of all, total momentum is always conserved. Experiment A is example of elastic collision, i.e. total KE conserved. Do we have to prove the momentum is conserved in both cases? I don't know. Let's just do the whole kinetic energy thing, shall we? So we can say that KE before is equal to, well, let's just say half MA UA squared plus half MB UB squared. So that's equal to half times, what have we got? 0.75. I'm going to write this down here. 0.75. And B was 1.25. So half times 0.75 times that. Oh, of course, the other one didn't have any kinetic energy, so we can forget about that. That's nice. So 0.2 squared. So in other words, 0.4. So that's going to be 0.015 joules. KE after is equal to half times that times, what's the speed? 0.05 squared plus half times 1.25 times, what was it? 0.15 squared. So let's do A first. So that gives us, well, let's say 9.4 times 10 to the minus 4 joules plus 0.014 joules. So we can say that this is roughly 1 times, or 0.1 times 10 to the minus 4. So we can say that this is roughly 1 times 10 to the minus 3, isn't it? And so that gives us 0.015 joules altogether. So that all checks out. Guess we need to do the same then for experiment B. Gosh, this is going to take an age, isn't it? They're going to want us to do momentum as well, aren't they? Fine, let's do momentum. Momentum, or we can say total P before, equals mv. So that is 0.75 times 0.2. And that gives us 0.15 kilogram meters per second. And we can say P total after, total momentum after, is equal to, oh, I've already got it, don't I? So let's say MA VA plus, but we've got to be careful with our signs, don't we? MB VB, so that is 0.75 times, what did it come back at? What did we say? 0.05, but it comes back, so I'm going to say minus for that one. Plus 1.25 times, I say 0.15. And so, if we do 1.25 times that, this gives us minus 0.0375 plus 0.1875. And sure enough, that gives us just bang on again, 0.15 kilogram meters per second. So we've done that. Then all you have to do is the same for the elastic collision example. So for experiment B, oh gosh, so let's go with kinetic energy first. So kinetic energy before, the half mv squared is the same, so that's still going to be 0.015 joules. And then K afterwards is going to be half MAB, so the masses combined, so that's half times, what are they together? The two altogether, 2 kilograms times their common speed, which is 0.075 squared, and that is not going to give us the same answer. Oh, there we go. So it's just going to be 0. So they just cancelled, don't they? So that's just going to be 0.075 squared, and that gives us much less than what we had before. So about a third of what we had before, actually. So let's say just 5, 6. No, let's go to the same degree of accuracy. There we go. So not conserved. And then we just need to do with the momentum as well. So momentum before, again, the total momentum was the same as in experiment A. So total momentum before was equal to 0.15 newton seconds, or kilogram meters per second. And then P total afterwards is equal to the mass together times the common velocity. So again, that's 2 times 0.075. And yeah, that is going to give us, as we can see, 0.15 newton seconds. So it is conserved. What a pain. That's like 8 marks calculation wise. Okay, back to normality. Golf ball, we have an FT graph. It's all going about the impulse, of course. We're going to have to find the area underneath. We haven't even looked at the question yet. We know we're going to have to do that. We have the mass. Calculate the speed at which the ball leaves the club. So therefore, we're going to say that the impulse is equal to the area under the graph. So that's just going to be 18 times 0.4 divided by 2, because it's, 2 triangles. So we can just do that. And so that's going to be 18 times 0.2, or in other words, 18 divided by 5. And so that's going to be 3.6 newton seconds. And we know that's equal to mv, impulse, or impulse is equal to change in mv, whatever. Therefore, v is equal to the impulse divided by the mass. So that's going to be our 3.6 divided by 0.045. And it gives us 80 meters per second, which sounds about right. 4, we have a wooden cylinder, we have a height, diameter, we have the density as well. Show the cross-sectional area of the wooden cylinder is about that. Okay, so we know that the area is equal to pi d squared over 4. So that is pi times 12 centimeters. Oh no, 2.9, whoops. So 0.029, so that's to be meters. Don't know why I did that. Squared, I'm making a mess of this, aren't I? Divided by 4. And sure enough, that does give us 6.6 times 10 to the minus 4. Next, calculate the weight of the wooden cylinder. We know that weight is equal to mg, but we have the density, so therefore it's going to be density times volume times g. And so that is, what was it? 400 times by, well, the volume, isn't it? So we know there's going to be density times area times height times g. There we go. So times by 6.6 times 10 to the minus 4 times by the height, which is 12 centimeters. So that is in meters, that's 0.12 times by 9.8. I think I can cancel some powers of 10 here. I'm going to take 2 off there, take 2 off there. Wasn't really worth it, was it? Can I just say 0.48? Totally not worth it. Whatever. Multiplying this all together, and we end up with 0.31 newtons. Easy. Okay, yes, we knew it was going to be floating in water eventually, didn't we? Calculate the distance, y. Okay, right, we know that upthrust is equal to weight of displaced water. And we know because it's floating, we know that's equal to the weight of the cylinder. Therefore, we can just say that the weight of the water is equal to mg. And again, we know that's going to be rho vg, so that's going to be equal to rho a, well, it's y this time, isn't it? yg. So there's a whole shortcut that we can take here, isn't there? So we know that the weight of the water is equal to the weight of the cylinder, the weight of the water displaced, that is. So therefore we can say that that is rho of water times the area times y times g, and then the weight of the cylinder we know where we can just say is rho c a h g. Yes, we can use the weight that we calculated earlier on, and we can do that, but there's no point. I think this way is easier, so therefore g's cancel. We know it's going to be the same area as well. Therefore, let's just rewrite this. We can say density of water times y is equal to density of the cylinder times the height. We're looking for this y here, so let's put the density of the water over the other side. So that's equal to, it was 400, wasn't it? Times the height, which was 0.12, because it's 12 centimeters, divided by 1,000. So therefore, we can just say that it ends up being 0.4 times 0.12. I think that's going to be something like 0.0048. Yes, didn't even need a calculator. Look at me go. Look at me. So yes, they've tried to fool you into using the weight there, but I think, you know, you need to recognize whenever it comes to upthrust questions, it's just weight of the object equals weight of displaced water. And then once you say that the weight is equal to rho vg for both, then you can cancel some things out and it all comes out in a wash. A lot easier. Student repeats the experiment but replaces the water with oil of density that. Calculate the new distance y. Well, we just found this out basically, didn't we? We had y is equal to rho c times h divided by rho of water or liquid, whatever. These two are staying the same because it's the same and it's the same height as well. Therefore, we can see that y is inversely proportional to the density of the liquid. I'm just going to call that rho. Therefore, we can say that y1, rho 1, is equal to y2, rho 2. We're looking for y2, so let's put rho 2 underneath there. So that's our 0.048 meters times by our initial density, which was 1,000 divided by 900. Sure, we'll cancel out some of these bad boys here. And that ends up being 0.053 meters instead. We need an explanation, so we can say it's the same weight of liquid displaced. But of course, because lower density, therefore greater volume must be displaced. Okay, so question 5, we have EMFs and all that jazz. What are we being asked? Use Kirchhoff's second law to show that V is equal to E minus IR. Kirchhoff's second law, of course, is total rises in EMF, rises in PD or potential equals, we probably should say sum of, equals sum of drops. So therefore we can say that, well, EMF is equal to V across R plus V across R. And so that's equal to E minus IR. Couldn't be easier. Classic, we have a graph of V against I, terminal PD. Explain how values for E may be determined and R, no calculation required. E equals y-intercept and R is equal to, well, let's say minus the gradient, shall we? Man, OCR papers are so much nicer than AQA, good grief. You should see the AQA paper from this year. Man alive. Resistance to the variable resistor is now fixed. Current is 25 milliamps. Use a graph to determine the resistance R of the variable resistor. Okay, so what we have to do is read off the graph. 25 milliamps is right there. And so that is 5.68 volts. There we go. So it's just V equals IR because we're just dealing with the variable resistor. We're not looking at the whole circuit. That's really important. When it comes to electricity questions, circuits, you've got to think, am I looking at the whole circuit or can I just deal with individual components? And at this point, we're just dealing with an individual component. So therefore, we can say that R is equal to V over I. We said that was 5.68 divided by 25 milliamps, so 0.025. So it's going to be times by 40. Essentially, I can't do that in my head. So probably could, but I'm not going to. And it gives us 227.5. Let's do two sig figs, 230 ohms. Calculate the energy dissipated in the variable resistor in 5 minutes. So obviously we want power first of all. Variable resistor, we know that P is equal to I squared R. We could of course go with VI. We could go with V squared over R. We have all of these things. Tell you what, let's go with VI. Why not? So we have 5.68 times 0.025. So in other words, divide by 40 this time. And well, that's power, but then in order to turn it into energy, we need to times by time. So times by 5 lots of 60, because it has to be in 5 minutes, doesn't it? It has to be in seconds, doesn't it? So 5.68 times that, and that gives us 42.6 joules. Let's go with 43 joules. They've gone with something different. How have they gone with something different? I don't know. I don't know what they've done there. I think that's just rounding error, to be honest. Yeah, I think it is rounding error, as long as your calculations are right. Calculate the charge passing through the variable resistor in 5 minutes, including an appropriate unit. Of course, you know it's going to be coulombs, don't we? Coulomb. Now, we know that current is rate of flow of charge, so therefore Q is going to be equal to IT. So we have just 0.025 again. Man, this is a really nice paper again. Times by 60. So in other words, I can do this in my head. 7.5. Yes, because it's 25 times 300 essentially. So 7.5 then divided by 100. So 7.5 coulombs. Cool. 6, table shows properties of an LDR. We have the resistance at various points. Point is that we have these different powers there, don't we? Design a circuit using a potential divider. Okay, so that the output potential difference is greater than 5 volts when the LDR is in very bright light, less than 1 volt when the LDR does not receive any light. Okay, so we're talking about an output PD, so I think we can just draw rails. I don't think we need to draw a power supply here. So that's generally how we draw these circuits. So we're going to have a fixed resistor there, then we'll have our LDR, not a very well drawn one though. And then we're concerned with this PD here, aren't we? Okay, so let's have a think about this. So when it's bright, the PD has to be, or sorry, the resistance is, or the LDR rather, is 2 times 10 to the 2 ohms. Okay, so if that's 2 times 10 to the 2 ohms, then that means that, well, we want it to be greater than 5 volts. So I don't know, what should we choose, like 10 volts up here? Is that a good way of doing it? Let's check it out. So if that's 2 times 10 to the 2 ohms, so when it's very bright, that means that we have high light, and so we have obviously a low resistance. So therefore, we want it to get more than half of our PD here. So I don't know, if we say that it's something like the resistance of this resistor is 1 times 10 to the 2 ohms. That makes sense, doesn't it? So that all checks out. So it's going to get, 2/3 of that 10 volts, isn't it? What about when it's dark? Well, I've chosen the wrong colours here, but whatever. So when it's dark, it's going to have 2 times 10 to the 5 ohms. See, this is the thing. They've duped us. It can't happen this way, can it? Because we need the voltage to be the other side. We need the voltage across the fixed resistor instead. That's how they got us. I was a little bit confused, and that's why. Because they got me. Whoopsie. So I tell you what, I'm going to swap round my LDR and my fixed resistor. I'm going to have the output PD there now instead. Right, that makes a lot more sense. Let's go for my 10 volts again. Let's go for my 0 volts again, shall we? So when it's very bright, this will have a resistance of 2 times 10 to the 2 ohms. And so this fixed resistor down here, it needs to have more than that. So let's go with something like 3 times 10 to the 2 ohms. Fantastic. Now, this bottom resistor will get more than 5 volts. So when it's bright, it will get 6 of those 10 volts. So that all checks out. What about when it's dark? The resistance changes to 2 times 10 to the 5 ohms. Now, the LDR will have a lot more of that 10 volts, and the fixed resistor will get very little. So, you know, like 0.001 volts. So it is much less than 1 volt. So yes, that checks out. So you just got to go through the process. When it gets dark, resistance, we want the voltage to change in a certain way. So you have to think, is the output PD going to be across your changing resistor or your fixed resistor? Are they expecting us to calculate it when it's bright? Okay, fine, let's do that. So we can say that, of course, V out over V total is equal to R over R total. So we're looking for this. So let's just times that by V total. So in other words, we have 3 times 10 to the 2 divided by 2 times 10 to the 5. And then we times that by 10. So I'll tell you what, I can just call that times 10 to the 3. And so, well, this ends up being then times 10 to the 2 on the bottom. So essentially 3 over 200. So that is going to give us something like 0.015. But it is less than 1 volt, and that's the whole point. 7, here we have, looks like photoelectric effect. Yes, an LED, it's still, you know, similar to photoelectric effect. Or is it just energy of photons? Maybe it is just energy of photons. Okay, we have this graph. We have this relationship. Okay. D is a constant. Okay. Show the gradient of the straight line of best fit is about that. So, you know, you're just going to make a gradient. I actually have to show you guys how to do that. Use the gradient from 1 to determine a value for h. Write your answer to 2 sig figs. Okay, so let's write down the equation again. So we have V is equal to hc over E 1 over lambda plus D. D is a constant. Okay, so we know that our graph was V against 1 over lambda, don't we? And so therefore, if we have this, if we equate it to y equals mx plus c, then that means that, well, if this is our x, if this is our y, then that means that's our c. So that means hc over E is our gradient. So we can say gradient equals, I'm just going to call it m, equals hc over E. Therefore, we're looking for h, therefore h is equal to em over c. So that's 1.6 times 10 to the minus 19 times by our gradient, which is 1.2 times 10 to the minus 6. So let's just call this minus 25. And then divide that by the speed of light, so 3 times 10 to the 8. And it looks like we are going to get, well, let's just say divide by 8. So that's going to be then 33. And then I'm sure we'll end up with minus 34 at the end. And that gives us 0.64 times 10 to the minus 33, or in other words, 6.4 times 10 to the minus 34. Not too shabby. Draw a worst acceptable straight line. Of course, worst acceptable straight line can be the highest possible gradient, or it could be the lowest possible gradient. I'm going to go with the lowest possible gradient here. They've been nice. The worst possible line is going to hit the top of this bar here and the bottom of this bar here, it looks like, but it doesn't always. It's going to be something like that. There we go. Determine the percentage uncertainty in your value for H. So you could end up with a higher gradient than the 1.2 that we had up here. So I think they're looking for something like a 0.2 difference. So I'm just going to say 1 times 10 to the minus 6. And so we know that percentage uncertainty is equal to the uncertainty, the absolute uncertainty divided by the value times by 100. And so all of these are times 10 to the minus 6, so we don't care too much. So 1.2 take away 1 divided by 1.2 times by 100. So it's going to be basically 0.2 times 100. So 20 divided by 1.2. And I end up with 17%. But whatever you do as your calculation, you will get the mark. Right, B, in a different experiment, photoelectrons are emitted. We have wavelength of that. Let's just put that in standard form, shall I? Put that in meters. So 9.8 times 10 to the minus, well, it would be 9, so it's minus 8. Work function is that, so that's our phi. Calculate the maximum kinetic energy of the photoelectrons. Right, so we know that EK max is equal to HF minus phi. And of course, well, we're dealing with wavelengths, so that's going to be instead HC over lambda minus phi. So that's going to be 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 9.8 times 10 to the minus 8 minus the work function, which is 4.1, but it is electron volts, so we have to times that by 1.6 times 10 to the minus 19. Beasty calculation. 8 on the top minus 8 on the bottom, so I don't know, so that's going to end up being 16. And so that ends up being, what's that, plus 16, so that's going to be 2418. And that gives me 1.37 times 10 to the minus 18 joules. Tell you what, let's go to 2 sig figs, seeing that our data is to 2 sig figs, so 1.4 times 10 to the minus 18 joules. Oh, last question already. The intensity of the EM radiation is now decreased without changing the wavelength. State and explain the change, if any, to the maximum kinetic energy of the photoelectrons. No change, as intensity only changes the rate of photons, what can we say, incident on plate. Is it 2 moles? Yeah, sure. Due to one-to-one interactions, electrons will still gain the same amount of energy, the same max KE anyway. Easy peasy. There we go. Hope you found that helpful. If you did, please leave a like. If you really found it helpful, please hit that thanks button. Really goes a long way to helping me keep making these past paper videos, because they don't get watched a lot, let's be honest. And if you want to see the rest of the papers, then click on the card and it'll take you to the playlist, and I'll see you there. Bye for now.